Hey class, welcome back to Behavioral Statistics. We are moving into chapter 7. We're pretty much at the halfway point of the textbook. In this chapter, we're going to be building on what we used last chapter with probability, and now we're going to look at probability in samples and how it relates to the distribution of sample means. So, oops, sorry. So by the end of the chapter, you should be able to define what distribution of sampling means are, describe distribution by shape, the expected value, and standard error. So another statistic we'll be calculating. Describe the location of sample means, mean of M by z-score, and then determine probabilities corresponding to sample mean using z-scores and unit normal table. So the tools that you'll need, random sampling, this idea that we talked about in previous chapters, being able to sample, randomly drawing samples from a population. We'll also look at probability and the normal distribution, and then as well as z-scores. So hopefully things that are by now pretty familiar to you. We're not diving into anything too new. We're just kind of reframing some of these tools that you already have learned how to use. So I want to step back for just a moment and kind of offer up a brief explanation of where we're going before we really dive in. We're going to be looking at the sampling distribution of the mean, really meaning we're going to be looking at all possible samples of theoretical samples from a given population. So all possible sample sizes of n. In this case, that would be, we're going to be working with a really simple data set here to start with, only one, two, and three, so data points. You can compute the statistics on those samples and then arrange the statistics in probability in terms of their distribution. So even if we have a simple data set that looks like this, one, two, and three, that's our population. We pull samples of at least two of n equals two from this population. And these are all the possible samples we could draw. We could pull a one and a one, a one and a two, a one and a three, two and a one, two and a two, etc. And these are X bar just means mean. So these are the different mean scores that we could possibly get. And then if we distribute all of these possible means here on an X and Y axis, we have the probability, and then we have the actual mean here. So we can see, the probability is highest for getting a mean of two, which makes sense. If we go in and look at all of our possible means, two pops up the most times with three, and then we have a bunch of scores that kind of hover around two. So it makes sense that that's why we're talking about. So this is kind of getting into the weeds of theory a little bit here, in terms of statistics, but why we're doing this, why we're trying to look at this is we're really starting to break ground into understanding inferential statistics. And remember, inferential statistics, we are trying to understand our population. Sorry, I moved the little cursor, I might have moved the slides away. We're trying to understand our population, which has maybe have a distribution like this, it could have a normal distribution, whatever. We pull sample sizes from that or we pull sample sizes, excuse me, and then we look at those distributions of means, and hopefully, they start to assume a bit of normality over time if we collect enough samples. So again, we have a population, we know the population's mean, and let's say we are pulling random samples from that population. We might pull sample one, which has its own mean, sample two has a mean, sample three has a mean, sample four has a mean. Now, hopefully those will start to cluster around our population mean. They should resemble, but we'll plot them out on this X and Y axis, and with enough samples, with enough sample size, they will start to look like a normal distribution. So if we have the mean of our population, again, pretty simple, one, two, three, we only have three data points. We add those up, divide it by the total number gives us two. We can find our standard deviation pretty quickly as well. We subtract, three from two, two from two, one from two. That's our mean. We square those values, and we get two-thirds variance. We square root that to get 0.82. We go back. What is the mean of our sampling distribution? Again, for these, we're looking at the same thing. We're looking at two. Our standard deviation is sampling mean of a third, variance of, or a variance of one third, standard deviation of 0.58. So pretty spot on. Our mean of our sampling distribution looks a lot like our population distribution, and that's kind of what we're trying to get into. So our rules for looking at the sampling distribution of the mean, our mean of our population is what our mean from our sample should look very close, if not identical, to our population mean. So that's what this is referring to. And previously, that other example, our sample mean 2 looks just like our population mean in this case of 2. The rule for standard for sampling distribution of the mean or standard deviation, you're going to take the standard deviation and divide that by the square root of n in this case. So if we take 0.58 equals 0.82 divided by the square root of 2, gives us 0.58 divided by 0.82 divided by 1.4 gives us 0.58 equals 0.58. So just some rules, kind of background of where we're going, and it might help. And this is also referred to as the standard error of the mean, and we'll talk about that later on as well. So the location of any score from our sample can be represented on a z-score. We've talked about like how far away it is from the mean. Researchers, however, are typically looking at also the entirety of the sample, not necessarily individual scores. So that's kind of what we're doing with this chapter is instead of focusing on individual scores, we're kind of taking more of a 10,000 foot view and understanding what's going on with the actual sample itself. So because samples, they're what give us that estimate of the population. Maybe we know the population mean, but through our samples, the data we collect, we can find out how close that sample represents the mean. And so we're going to be looking at a procedure of being able to transform our sample means into z-scores as well. We've transformed individual means into z-scores. Now we can do the same thing with sample means. Really not asking us to do a whole lot more. We're going to be looking at this topic called sampling error, because remember, we're pulling samples from populations, and it very rarely is it going to be this identical. Like what we're going to have is some kind of natural occurring discrepancy, or what we refer to as error, between our sample statistic and the population parameter. Error does not indicate a mistake was made by any means, anything like that. It just means we have variation. Samples are prone to variation. They're variables. Two samples are very rarely identical. Even if we're pulling from a population that's pretty similar, our samples are probably going to look different. So we want to be able to capture that sampling error of going from population to sample. So two different samples will probably be different, even though they are taken from the same sample population. Especially if we're talking about random sampling, it's really unlikely that the sample means would be the same. The distribution of all sample means in our collection for the possible random samples of a particular size can be obtained, and this is in this case, lowercase n, and we're looking at, okay, if we get enough of these, they start to look normally distributed, kind of like that graph I showed you at the very beginning. So distributions earlier, we were referring to distributions of scores from sample. Now we're looking at a sampling distribution of statistics. So the sampling distribution of means. A distribution of means is a special kind of population. It's obtained by selecting all the possible samples of a specific size, in this case n, lowercase n, from a population. So, and ultimately, if we collect enough of these, they should start to pile up around our population mean. They'll start to look like that normal distribution. And it tends to, the distribution of sample means tends to be normal in shape. The larger our sample size, the closer the sample means and that will be to the actual population mean. So right now, this is a pretty simple graph. Maybe we only have 4 scores here. And so we're not really seeing much clustering, but if we start to get enough samples, instead, we have our sample means. Instead, we can start to see the possibilities. Even if we pull out, 2 scores, n equals 2, we can still start to see the different values they're taking on. Especially, if we only have 2, 4, 6, 7, and 8, we have all kinds of possibilities of means here with this distribution. And again, with enough sample size, it starts to look more normally distributed with most of the data kind of here in the center, most of the outcomes. So it's possible to determine exactly what the distribution of sample means looks like without taking hundreds and thousands of samples. That's kind of getting into some math here called the central limit theorem, and it's really used how we can understand the shape of our distribution without collecting all of the samples. We can in fact do it with around 30 is kind of the rule for this case. So the central limit theorem is a mathematical theorem that says as n, in this case, our number of sample sizes, as it moves towards infinity, as it grows larger, our sampling distribution of means starts to approach normality. So what does that mean in terms of infinity? Well, really, we just need 30. At least 30 is when it starts to look more normally distributed. More on the central limit theorem. It really applies to any population. If we know the mean and standard deviation, our distribution of sample means approaches a normal distribution as n approaches infinity. And then we measure that with we'll look at that as the mean of m in this case, and our distribution of sample means for sample sizes of n will have a standard deviation of, in this case, standard deviation divided by the square root of n. So again, that standard error formula we talked about previously. So more about the shape of our distribution. The distribution of sample means is almost perfectly normal in either two conditions. The population from which the samples are selected is already normally is a normal distribution. So if we're already working from a normal distribution, those sample means should start to resemble that as well. The number of scores in each sample is relatively large, at least 30. Again, kind of satisfying that central limit theorem. So, how do we calculate this? We have the mean of our distribution of sample is the mean of M. In this case, what we're looking at has a value equal to the mean of the population. The mean of the distribution of sample means is called the expected value of M, capital M, and we consider this an unbiased statistic because we have the expected value of the distribution sample means is the value of our population mean. So they match up. It's kind of going back to that rule, one of those two rules I showed you earlier on in the slides. So finding the standard error of M, this is a measurement. Standard error of M measures how well an individual sample mean represents the entire distribution. We're trying to find out, so a larger value indicates more error, means it's not as representative. A smaller value means it's more closely aligned to that population. Variability of distribution of scores is measured by our standard deviation, and variability of a distribution of sample means is measured by the standard deviation of the sample means, and this is called standard error of M, and also written as standard deviation of M, like it's written here. So you have a couple different ways you might see it depicted in your textbooks or these slides. The standard error of M is the standard deviation of the distribution of sample means. When it is large, it means the means are widely scattered. When the measure is smaller, obviously not as much. So the standard error of M provides a measure of how much distance is expected on average between our sample means, that our standard error, and our actual mean. So this is getting back into the law of large numbers. The larger the sample size, the more probable it is that the sample mean will be close to the population mean. And in terms of variance, population variance, the smaller the variance in the population, meaning they're going to be much more closely resembling statistically, the more probable it is that the sample mean will be close to the population mean. And so here's that relationship reflected here, where our standard error is much higher when our number of scores in the sample is smaller, but as that gets larger and larger, we can see the error rate going down precipitously. And so here's some different distributions. Maybe we have these scores here. We pull a random sample. This is our original population of IQ scores. We have 100, mean of 100, standard deviation of 12. We're looking for, okay, this random sample of 16, here they are. What does that look like? We get a mean of 100, pretty close. We get a variance of 9.88. We can square root that. And it still looks normal in terms of distribution size. It's still pretty comparable to our sample. The sample we pulled is pretty comparable to the mean that we used. Okay, let's do a quick comp check, make sure we understand before going on. A population has a mean of 60 with a standard deviation of 5. The distribution of sample means from our samples is n equals 4. Selected from the population would have an expected value of what? Is it A, 5, B, 60, C, 30, or D, 15? Pause the video, write your answer down, or kind of work through it, and maybe try to understand why you're coming up with the answer you did, then return to the video. Okay, hopefully you've worked that through. The correct answer is B, it's 60. If we know the population mean is 60, our sample mean should be pretty close to that, if not exactly 60 as well. Okay, couple of true falses. True false, the shape of a distribution of sample means is always normal. True or false, as sample size increases, the value of the standard error decreases. Go ahead and pause the video, work through it logically, what you think the answers are, write down your answers or document it somewhere, and unpause the video and we'll do a comp check. Okay, hopefully you're back. Hopefully you worked through both of those. First one is false. It is normally only if the population is normal or n equals 30 or greater than 30, I should say. And then the second item is true. Sample size is the denominator of the equation. So as n grows larger, standard error decreases. That's kind of that relationship. Sample size grows larger, we tend to see a smaller standard error. Okay, so the scores and probability for sample means, or z-scores, excuse me. So the primary use of our distribution of sample means is to find the probability of selecting a sample with a specific mean. Proportions of the normal curve are used to represent probabilities, and we're creating z-scores for for the sample mean. We're trying to compute z-scores again. And here's our formula. We're going to take m minus the mean, giving us the standard deviation of m. So you're working with two different equations here for this one. You have this equation obviously, but don't forget to find standard deviation of m. Sorry, we've got to perform this procedure here. Standard deviation divided by the square root of n. So keep that in mind. That'll be useful later on. Okay. So that's our formula, pretty similar to our formula we used for z-scores in the previous chapter. So we can start looking at things like, okay, if the mean is 500, and the standard deviation of m is 25, if somebody scores a 525, what does that look like? We can look at the middle 80% of a distribution of sample means, so we can start to calculate those things as well. So adding on to that standard error, usually there's going to be a discrepancy between our sample mean and the population mean. We call that sampling error. The amount of sampling error will vary across different samples, random samples, of course, and the variability of sampling error is measured by the standard error of the mean, which we talked about in previous slides. Smaller number, better. This is a distribution of all possible sample means and standard errors as well. And this is what these our distribution might look like. Even if we have a sampling, if we pull three samples from this population, they all have a mean of 80, but depending on the variance, we're going to see different rates of standard error. We're going to see more pull. We're going to see more variation. So as our number goes up, we're going to see much less. We're going to see much less variation, much less standard error in this case, going from n of one, n of four to n of 100. We can see now all three still maintain the shape normal distribution, but in terms of reducing the standard error, we can see by the time we get to C, it's been cut down quite a bit. Journals will report standard error. Usually, you might see it referred to as standard error or standard of the mean. It's usually reported along with your sample size and as well as n, and may also be included in some kind of bar graph or line graph. You might see examples of that. So here, we might see this, your M score plus or minus standard error of the mean. We have group A, group B. We can see that their performance number of mistakes. We can see the standard error. We can see it going down, group B versus group A. There seems to be a pretty noticeable difference between our two groups. And this is what allows us to kind of get into inferential statistics, which we're going to cover next chapter. We're using samples to understand population. Sample information, again, it's not always perfect. It doesn't always match the population. So there is that degree of sampling error. And we're trying to statistically kind of catch those natural errors and differences that occur between our sample and population and really trying to map out our degree of uncertainty. So maybe we have a population of rats, we're trying to study. They have a mean of 400 and standard deviation of 20. We pull a sample of 25 rats. We conduct the treatment. We have our treatment of 25 rats. We want to know, like, especially if there is a significant difference, in the rats who received treatment and those who did not, we want to make sure the probability that our sample actually is reflective of our population. So maybe this is what this might look like of the rats we have, with a mean of 400, we collect data on 25 and we can see some are going to score in the lower end of both tails. Most of the data is going to kind of toggle there towards the middle. Okay, let's do another comprehension check. A random sample of n equals 16 scores is obtained from a population with a mean of 50 and a standard deviation of 16. If the sample mean is 58, the z-score corresponding to the sample mean is what? Is it A, z equals 1, B, z equals 2, C, z equals 4, excuse me, or D cannot determine? I'll go ahead and spoil it for you now. It's definitely not D. We can determine it, but you may want to pause it and do the math yourself before coming back. Okay, so hopefully you paused it, you worked it out, and hopefully you got B. So if we go back to our equation, sorry, if we go all the way back, we have our equation. So our sample mean is 58. We're going to subtract that from our mean of 8 or 50, excuse me. So we'll have 8 on the numerator. Remember, in order to get our standard deviation of the mean, we got to go back and we have to run this equation. So our standard deviation divided by n square root of n. So in this case, sorry, getting back, we have a standard deviation of 16 divided by the square root of 16. So that's 16 divided by 4 is the denominator. Our numerator is 8 divided by 4 gives us 2. So hopefully that worked out for you. Next one, a sample mean with z equals 3 is a fairly typical representative sample. True or false, the mean of the sample is always equal to the population mean. Go ahead and pause here. Make sure you understand before moving forward. Okay. First one is false. A z-score of 3 is an extreme or unlikely score. And then 2 is also false. Individual samples will vary from the population mean. All right. So that's really it for chapter 7. That's a lot I threw at you, but hopefully it makes sense. If not, please send me questions. Please post questions as comments. Please don't forget the homework and the practice problems as well. I think that'll help clear up any confusion you might have. But that's going to be it for this week. Be good and be safe. I'll see you on the other side for chapter 8. Take care. Bye.